Okay, thank you, Alicia. It's really a great pleasure for me to introduce Francesca. She was born in Naples, in Napoli, so she's from the same general part of Italy as my people are. She got her master's in physics, working both in Napoli and in Trieste, studying the theory of Bose condensates, and then she went to Firenze to get her PhD with our friend Massimo Nguscio, and she did pioneering work in Bose and Fermi gases there. And from Florence, she went to Innsbruck, and she's described her experience there as intending to stay there for a few months, and it just kept getting extended and extended, so that now she's a full professor in Innsbruck. When she first got there, she worked with Rudy Grimm, and she did the famous Efimov experiments. She eventually started her own group, and she got famous doing dipolar cold gases and other neat stuff. And along the way, she accumulated all sorts of awards and recognitions, which I'm not going to list. But the one I like best is the Junior BEC Award, because this is given by the conference that's held every 2 years in San Feliu, and it's given by the people who know this work best. And so I think that it's really a great award. Well, today she's going to talk to us about supersolids, and I'm really looking forward to this because there's been so much that has been said about supersolids over the years, and a lot of it's been, how shall I put it, foolish. And so I'm really looking forward to hearing about the real deal. Francesca.
So, Bill, thanks a lot for this very nice introduction, and thanks for the nice invitation to this colloquium. It's really a great pleasure for me to be here, even in this virtual form, of course, in 2 dimension. And I would like to take now the opportunity to let's say, focus my talk on a very specific topics of research that was going on in the last couple of years in my lab. And so, as Bill said, is the observation of a supersolid made of dipolar particle in a Bose-Einstein condensate, let's say, quantum gas of bosons, using erbium. And I like this topic very much because for us it was really like a puzzle to try to put together piece by piece the different ingredient we would need to see this state, and many things came really unexpected and actually unexpectedly easier than what we have thought. And so this was for us a fantastic adventure, scientific adventure. And so that's why this topic is very close to my heart, also because it's rooted on the fundamental understanding of quantum fluid. So I will try first to give you an overview of what are the important ingredients that we kind of rule out or that we think are important to observe a supersolid state, and then to show you also some very fresh results. Some of them have never been shown before publicly, so let's see how it goes. The first problem in speaking about supersolid is a problem of visualization. So what is a supersolid? Well, a supersolid is a very counterintuitive state of matter, is purely quantum, and it's very counterintuitive because now the particle that compose your quantum system, your many-body quantum system, actually share 2 properties at the same time that one would typically consider to be antithetically. So in this system, so you have both, let's say, a crystalline order, which is typical of a solid or of a crystal, and at the same time, so you have the properties of superfluidity in the sense of a frictionless flow. So it's a kind of very strange state in which at the same time so you have crystalline properties, so you are breaking, the system is spontaneously breaking translational symmetry by, let's say, building up some order in space, crystalline order in space, but still, because the particles are all identical, the bosons are all identical in our system, they can also be fully delocalized and flow as a superfluid. So our best way to visualize this state is actually going to the Greek mythology and to get inspiration from a Greek god, which is called Janus, that is a god having two faces at the same time. And so the god itself was looking to the future and to the past at the same time, while our interpretation of Janus is a god that is both a crystal and a fluid. And the key ingredient is that it's not possible to describe a supersolid in terms really of, let's say, two-component system, the crystal component and the liquid component. So you cannot remove one of these components without destroying completely the state. So it's the coexistence is a very important ingredient. And I mean, of course, if we think about quantum fluid, so let's say many-body quantum system with interaction, we have very important example, which goes from, let's say, in solid state, like superconductor, or thinking about a liquid, it's a helium superfluid, or our gas state as our Bose-Einstein condensate, and even now polariton. In all these, quantum fluid interaction play a very important, let's say, and crucial interaction. And in thinking about this state, there have been over the year, so almost 60 years ago, the question whether one state which is solid can also share the properties of superfluidity. And this is where our story kind of start. Indeed, it was Gross, I mean the guys from the Gross-Pitayevsky equation, that in 1957 was writing a paper about a unified theory of Bose-Einstein condensate system, and he kind of showed that indeed it might be possible to have a solid which also shares superfluid properties. Now, this type of question then was echoed and was, let's say, further investigated by many theorists, but still the question remained from a theoretical point of view extremely debated over the year. Indeed, there was a point of view back in the 57 by, for example, to name one, Penrose and Onsager, in which there is the idea that Bose-Einstein condensation in a solid is actually not possible because you have the competition of order. Let's say the localization which is required in a solid would compete with the superfluid order. So the two symmetry, one defining the solid, let's say the translational symmetry, and phase properties, which is the gauge symmetry, cannot be, according to Penrose and Onsager, cannot live together, but they are rather two competing order of a quantum state. While then Gross, as I mentioned, and many others, including Chester, they kind of started to make the first speculation and then more, let's say, rigorous derivation that actually it would be possible in a solid to have both crystalline order and Bose-Einstein condensation. And the point of view of this early work, including the one of Leggett in 1997, was really the question, can a solid, so starting from an object having, let's say, the properties of a solid, whether by cooling this solid would be possible also to make emerging superfluidity. If you have, for example, interstitial defect, or you have vacancy in a solid, whether this vacancy or defect can be, if they are of bosonic statistic, they could both condense and move, but by moving a vacancy also oblige the let's say, the fillet site to move, and this creates a very strong correlation of a single object. So it was indeed a very debated theoretical question, and from the experimental point of view, it took a while to really try to answer this question, and the first answer to this problem actually came rather recently, I would say, with the observation by Kim and Chang in solid helium of a probable observation of a supersolid helium phase. And this was by starting with solid helium. Indeed, after 1970, the system under intense theoretical investigation was helium solid, because the quantum fluctuation in this system is they are very large, and because of this quantum fluctuation, it was speculated that superfluidity could appear in the solid phase of helium. And so in 2004 there was this Nature paper with the probable observation of a supersolid phase. Now, this was a very remarkable and difficult experiment, I would say, and of course polarizing the attention of the community, and both on the experimental and theoretical side. So in the experiment, several groups have tried to repeat this measurement, which was based on the measurement of non-classical moment of inertia. That was, let's say, a Gedanke experiment suggested by Leggett in his 1970 paper. But somehow the observation from other groups was not really matching the one of Kim and Chan. And also there have been different theoretical school of thinking, one more, let's say, in favor and the other in disfavor of the interpretation of the experiment. And it took really a very rigorous work by the same author and by the community to end up a few years later, actually in 2012, to the conclusion that this early observation was not related actually to supersolidity, but was rather connected to, let's say, the stiffness of the material and imperfection into the material considered. And so then after 2012, of course, the question whether a solid can be superfluid could not be answered positively. Now, we don't know if in the future it will, but at the moment that's not the case. And so the community interested in this supersolid state started to kind of shift the point of view. Instead of asking whether a solid can be a superfluid, the theoretical proposal started to appear asking whether a superfluid can be a solid. And this is a completely different, let's say, question somehow, because one would start from a state which already owns superfluid properties, or it's already both condensed and interacting, and eventually whether the interaction would kind of impose a crystalline order to the system. And there have been over the year, I'm just naming some of the author that have published on this subject, but I mean the list is very long, and many papers are really visionary in this sense and very beautiful. And so now in asking whether a superfluid can be solid, one has also to ask which are the properties that this superfluid, can any superfluid, or do we need specific, let's say, innate properties of the superfluid such that they can show, let's say, some translational breaking, so the breaking of the translational invariance, so the creation of a crystalline order. And now the answer is actually, it's, yeah, you need the specific properties of the superfluid to start with. And the properties is that this superfluid state, whatever it is, should have the constituent interacting, that's okay, but this interaction should have a momentum dependence, okay? And so now I like this picture of the sea. You have to imagine a quantum fluid in the bulk, let's say very big, let's even, if you can dream, even homogeneous, which is not what our experiments are doing, of course, but let's say in a bulk, and then there is some interaction which have a dependence on the momentum. So the dependence of in momentum space will give you in real space a sort of preferentially wavelengths that can set in a sort of order in the system and so in space, like crystalline order or a periodic structure in space. And so now not all superfluid can match this requirement. And the platform in the, let's say, in the realm of neutral atoms or ultra cold molecule have been the following. So the platform studied, so like Rydberg gases, where the dipole-dipole interaction can be very strong, or for example, you can have light couple Bose-Einstein condensate or spin orbit couple Bose-Einstein condensate, in which in both of these, when you have light in one way or the other that couple to a BC that would interact via non-momentum dependent interaction, this coupling with light can actually create or induce in the system a momentum dependence. And so those are the platforms which are very intensively studied in theoretical proposal. And few years ago, let's say in 2017, it was possible in the group of Tillman Esslinger and then also in the group of Wolfgang Ketterlein to observe a state which have sort of supersolid-like properties. What I mean with this is that it was possible to see that the state would spontaneously break the translational symmetry. However, the specific K vector or K dependence was externally imposed. So then the meaning of spontaneous has to be taken with caution somehow, because the state which would break the translational symmetry, let's say, and create a sort of crystal is totally incompressible. So you don't have phonon, it's a very stiff object, and it's incompressible because the wavelengths, it's fixed externally. And so our system is a little bit different. We are focusing on dipolar quantum gases. Now, in the case of dipolar quantum gases, a little bit, it's a different point of view, because we are not really engineering a momentum-dependent interaction, but the gas itself, has very important dipole-dipole interaction, and the dipole-dipole interaction, which is really coming from the fact that, let's say, the atom have a magnetic moment, this dipole-dipole interaction have a space dependence very specific, so it's indeed long range. And if you do the Fourier transform, so in momentum space, there is a momentum dependence. This interaction in particular is not only long range, but it's also anisotropic, meaning that there is also the strength of the interaction is dependent on the orientation, on the relative orientation between our dipole. And so as a consequence, you can see that you can favor the attractive interaction, or you can favor the repulsive interaction just by shaping the trap and the confining potential in which you are loading your atom. And so dipole-dipole interaction provide, let's say, a very genuine case of momentum-dependent interaction. Now, in addition to this, the dipole-dipole interaction, it is not the only source of interaction among the atom. You also have the contact interaction, like in alkali atom. And this interaction is extremely important. You can see it's not, it's really contact type, so there is no extensive dependence on space, so there is no momentum dependence coming from the contact interaction. But it's very important that you have both interaction and that you have a mean to independently sort of control one or the other. And so in a dipolar gas, if you now think about the Fourier transform of the dipolar interaction, if you are in a uniform case, so you are not shaping the interaction by shaping the trap, then you have a momentum dependence just in terms of an angle. Okay, so there is no direct K dependence in a uniform gas. But if you put, let's say, in pancake or cigar-shaped type of trap that you are also, you know, favoring one orientation of your dipole with an isotropic confinement, suddenly this interaction also depend directly on K, not only via the angle. And this is, let's say, our case. So another important...
Francesca,
yes?
I I just want to ask about the kinds of things that are possible K-dependent interactions. Now, as you point out, if you've got a contact interaction, at least in the approximation that it is in fact a contact interaction, there's no K-dependence. But of course, that's only an approximation. And when we think about contact interactions and scattering lengths, then if we go beyond, say, the threshold behavior, then there is a K-dependence of the usual kind of interaction. And what I'm wondering is that sufficient? That is, what kind of a K-dependence is needed in order to make this happen? It's not just any K-dependence, I imagine.
So I think it's pretty, so the level of K-dependence, it's pretty broad, the class of K-dependence, but the problem, the point that it's also crucial is that you, so in the, for example, in the dipole-dipole interaction, it's a K-dependence, but you don't have, let's say, a specific K-star dependence. The K-star, so the specific, let's say, a special K, let's say, it's coming out because of the competition of the different energies. So you need to have different sources of energy in which some are attractive, some are repulsive, in order that in the energy spectrum you can create a minimum at large momentum. And the specific minimum is what is setting you the crystalline order. Right.
Okay. Good. Thanks.
Yeah, exactly. So and in the case of dipolar gas, you have the contact and it should be also strong somehow. So you need to be able to have a strong enough momentum dependent interaction to do this game. And so and regarding to this, I mean, for a long time, the Bose-Einstein condensate available in our lab had, of course, a non-zero magnetic moment, like also the alkali or chromium, but this so the corresponding dipolar interaction was not strong enough with respect to the confining energy or the kinetic energy or the contact interaction. And so the balance was not proper. So you need really a windows in which all the interaction are playing simultaneously in order to, let's say, have a minimum in the spectrum of excitation. But then in 2011 and then in 2012, the lanthanide atom, which are atomic species with relatively large magnetic moment, and also they are pretty heavy, came to the market first with the Bose-Einstein condensation of dysprosium in the group of Benjamin Leff, and in our group the condensation of erbium. And then this novel, this gave a much larger windows where we could change or use our parameter, and this made really an important change. Now, if you have a total interaction which is momentum dependent, and you look at the let's say energy of the excitation, let's say you can call this dispersion relation, so energy as a function of momentum, you see that this is in a very simple approximation. You see that also that there is this interaction part, which is momentum dependent here. And so if you now want to find the minimum of this function, you would find the minimum at k = 0, which is, let's say, the trivial case, no excitation. And then, but also another solution with the local minimum at a large momentum. And this local minimum is very reminding us very much about the minimum that you can see in helium superfluid. Although, let's say in helium superfluid, the interaction are of very, very strong and of different nature. But you see this minimum in the dipolar gas, which have been predicted by Luis Santos, Maciek Levenstein, and Jorasz Lapnik back in 2003. And this is very relevant, because what does it mean? It means that there is a specific value of the momentum, which I would call it K Roton, and that this specific value of the momentum, it costs less energy to excite your system. And there have been a lot of also in the context of helium superfluid, now the interpretation of what is this Roton. Actually, the name itself was introduced by Landau because he thought that this minimum was a ghost of a vortex. But then later it was realized that it's not the case, and Nozière very poetically called this minimum the ghost of a Bragg spot. So it's kind of a Bragg spot is what you have when you do Bragg spectroscopy on a crystal. And what Nozière wanted to tell us is that this minimum tells you that there is a specific interparticle distance which is preferred, and the atom have a tendency to organize themselves with this spacing like in a crystal. So the Roton can be interpreted as the tendency of a system toward crystallization. And this is a very key ingredient for supersolidity, because this minimum introduces special K, and the special K is the one that will set the crystal spacing when you break translational symmetry. Moreover, in our gas, differently from helium, the gap, the energy gap at this minimum, which is the Roton gap, can be tuned just by playing differently the competition between the contact interaction and the dipolar interaction. So by decreasing the contact interaction, which is repulsive, and so you can decrease this Roton. And so we could observe years later, almost 15 years after Luis Santos and co-worker predicted this, that indeed in our system, you have the clear appearance in the excitation spectrum of a uniform Bose-Einstein condensate, so of a non-modulated normal Bose-Einstein condensate, the spectrum of excitation create spontaneously this Roton minimum. And we measured the spectrum of excitation by using Bragg spectroscopy. But now, you see, if I now decrease even further the scattering length, and it took us years in our experiment to really learn how to control the scattering level, the scattering length as the level below 1 A0, I have to say. These are all, a lot of work behind that need to be done for this full control of the spectrum. And then what you can achieve is a situation in which the Roton mode soften completely. So suddenly, you don't need any energy to excite the Roton excitation. So it's simply, you don't need energy. So the system is unstable with respect against the excitation of the Roton mode. Now, within the Bogolyubov picture of the spectrum of excitation, when a mode gets soft, then what you have are instability, because since you do not need any energy to create this excitation, the system just by small thermal seeding or quantum fluctuation can start to populate this mode. And as soon as this mode is a little bit populated, then you will have exponential increase of this excitation, and the system would collapse. So, and this would be a collapse similar to the one observed in a contact interacting Bose-Einstein condensate, but at a larger momentum. And so this is also what we observed now in the system is the following. As soon as the Roton mode soften, then you would see that the system has to develop a little density modulation. And then the strength of this density modulation should increase maybe with time because of this exponential increase of the Roton population. But as soon as in TREP you have a density modulation in real space, when you map the momentum distribution, and you can do this just by letting the cloud expanding and doing time of flight imaging, which is the standard imaging by now in all experiments, you would see a self-interference of this density wave and a very clear interference pattern. And this is actually also what we observed when the Roton softened, that the ordinary time-of-flight image of a single peak was dramatically modified, and we saw the appearance of side peak, which signalizes that we are now populating a very specific mode, which is this Roton mode. And this is the momentum distribution. So we have also done a lot of, let's say, calculation, which agreed with this observation. Now, I don't want to go to this early case, but maybe one point is that our expectation, this we observed back in 2018. And so our expectation was indeed that now the Roton is created, and according to the Bogolyubov picture, we should see this mode to exponentially increase. And actually, what we observed is that the amplitude of this model was indeed increasing very fast, sort of exponentially, but then what we saw already back in 2018 is that the speed at some point start to, slow down. And it seems that the system, that the excitation was not proliferating anymore, but rather staying either constant or decreasing. Here we had also 3 body losses in this experiment, but kind of the very fast increase was stopping. And so back in 2018, we kind of already signalized that this Roton could be an entrance door to a change, a phase transition to a new ground state, which would be a modulated ground state like the one in supersolid. And indeed, if you now look at the density distribution observed, so in the green part, the ground state of the system is a non-modulated Bose-Einstein condensate, and on top there is the Roton excitation. And then at some point, now that we have the full theory, what is expected is that the system do a phase transition, and the ground state itself is not anymore, let's say, inhomogeneous and non-modulated, let's say, but it starts to be density modulated. And the modulation wavelengths is exactly the same of the Roton. So actually, just by looking at this absorption image that we had back in 2018, one could not really distinguish between these two cases. And so now, why this lower dynamic appears? So why it's not simply an excitation, but something else happens and the system seems to stabilize now in this modulated state? Well, today we know that the reason is that in this system, quantum fluctuation can play a very important role. So quantum fluctuation is an additional term that you have to put in the Gross-Pitaevsky, which have a faster dependence in density than the normal mean field contact and dipolar interaction. So what does it mean in practical? It means that when you have, let's consider just one specific case in which you start with a dilute Bose-Einstein condensate, and then you are now decreasing the contact interaction, and you have a system in which now the contact interaction and the dipole-dipole interaction are of the same order of magnitude. Then since the atom can decrease their energy by peeling up, because in this direction the dipole-dipole interaction is attractive, they would try, to create a very, very high peak, much denser than the ordinary Bose-Einstein condensate. But then quantum fluctuation is like a cutoff. It is a repulsive interaction and set the maximum height of this peak, stabilizing the full system that cannot grow in an infinite line, should stop its height. And this is really these 3 ingredients, so momentum-dependent interaction, the Roton, which is driving the system toward crystallization, and the mechanism that make that the Roton population don't diverge but stop at some point, are really all the important ingredients that are seeding now the the supersolid state. And this is what actually was then confirmed and observed in my group and in the group of Giovanni Modugno in Pisa and the group of Tilman Fau in Stuttgart. We got almost simultaneous paper in APS journal. And what we observed is that an ordinary Bose-Einstein condensate, thanks to these three ingredients I mentioned to you, would form a sort of spontaneous periodic modulation. That's really a gas. And this gas acquire a distribution in space, a density wave, which have nothing to do with the container. So they have its own shape. They break translational symmetry by creating this density wave. Of course, it's not an infinite density wave, it's limited. We have a finite size system. And now to go back to all these ingredients together, I like it very much what our postdoc Matthew Norcha have done a little animation, very simple to visualize what is going on. Now, let's start with magnetic atom, dysprosium, like the one we have now in the lab. And then this dysprosium are all, let's say, unlined in this way. So it's, however, a 3D object. Now, because dipole-dipole interaction is attractive along this side, all the dipole would tend to align like this. But then you have the repulsive contact interaction that make this blob a little bit more fatter and shorter, plus quantum fluctuation and the confinement. And so it's energetically favorable for the system to create this little number of droplets. And then by just carefully changing the contact interaction, you can change the link strengths between this kind of droplet, making that they all touch and they can, let's say, lock in phase, having global phase coherence. That's, let's say, I think a very nice visual interpretation of what it is a supersolid. And this is what actually we observe in our experiment. And the strengths of the overlap between this droplet, actually that you can think and use one wave function to define one droplet and the other one the next droplet, you can define an overlap, which is a strength or a link between the droplet, or a density bridge, or connected, if you like, the Josephson junction picture connected with the Josephson tunneling. And the strengths of this link from red very high to blue 0 will define now what are the phase coherence in the system. And we can calculate completely the phase diagram of our system, and then you would have a uniform Bose-Einstein condensate. And if we change for a given atom number the scattering length, but maybe low atom number, we have just single droplet. But if we have a little bit higher atom number, you can have an array of droplets where the density link is very small, so this S parameter is almost 0, or you can have this very nice pink region in which you have enough overlap between the density modulation that the phase coherence is completely preserved. And in our experiment, how do we probe all this? Well, we have two observable. A new observable for us is the intrap imaging. So we can really do in situ imaging and see the droplet and also see the link strengths between this droplet. And we can do time of flight, where we can recall the interference pattern as the one I show you. Here we just worked a lot in the lab to have really nice interference pattern with very high visibility of the side peak. And these two observable that we can have in our lab give you complementary information. So the in situ imaging tells you about the density modulation, and we have a resolution at the micron level. So each droplet is about 2 to 3 micron, and also the distance is few micron, can be between the distance between the peak. Or you can do time of flight imaging, which is the equivalent of having a matter wave interference, and look at the phase coherence. And these are now the simulation, and everything agree actually very well. But now I want to point out that the majority of these early experiments have been done in the following way. So we first produced, and this is the same also in the group of Stuttgart and Pisa, a Bose-Einstein condensate, which already have let's say, global phase coherence. And then we just changed the scattering length and crossed this transition. And so the appearance of a density modulation. So this change of interaction across this phase transition is never really adiabatic. So it's a sort of slow quench that one has to create. But actually in different experiments, included ours, what we saw is that by doing this crossing, one also excites in an important manner collective excitation of the system. So you have really some phase excitation just by the fact that we are crossing. So it's a nice way, but has this drawback of, let's say, bringing in also some phase excitation, because the supersolid now is a gas and is completely compressible, and you can have phonon mode of different type. And regarding this, one can say, okay, this is now the phase diagram, which tells you what is the ground state. And the next natural question related to phase excitation is, what is the spectrum of excitation of a supersolid, of this type of pink? Spontaneously created density wave modulation in our BC. And what is really amazing is that here the supersolid break two symmetry, the translational one and the gauge symmetry, by setting one single global phase into the system. And for each breaking of the symmetry, the spectrum of excitation should show a branch. And here we did our calculation for our finite size system of the spectrum of excitation. And when you are in the supersolid state, you really see the appearance of two branches. And also, if you have in mind now, let's say the Bragg, the Brulin zone in a crystal, you see this is all periodic repeated branch, like similar to a crystal. And so we could see the different nature of the moda. For example, you have crystal moda, which is a moda where just the peak are moving, let's say like an accordion in some sense. And then you have the superfluid mode, which are lower in energies, usually this lower branch here, in which you don't have really this type of, accordion motion, but more what you have is that the height of the peak is changing, telling you that there is flow of particles from one droplet to another droplet. And since I want to show the new result, I just flash here that by changing the scattering length from an ordinary BC to the supersolid state, we indeed saw that one single mode of the BC was start to be very perturbed and create two different branches of this specific mode, which was in this case a compressional mode, in which you have compression in the sense of moving like this and compression in the sense of the height of the peak changing. And we could really separate and showing the existence of these two type of branch into the system. And now let me flash briefly in the latest news from our lab, and one is regarding to the life cycle of a supersolid when we directly don't do an interaction quench, but we enter really by reducing the temperature into the state. And the second is really a very fresh new result about going to the supersolid. So what I explained so far is the possibility to create a supersolid by quenching the interaction, but actually, and this is the phase diagram is well, so we know how to calculate pretty well, and it's kind of benchmarked with the experiment, and it's fitting reasonable well. But now there is another way, and there is another dimension of this phase diagram, which is the one more, standard, how the first Bose-Einstein condensate was produced by really decreasing the temperature. So we would do a direct evaporative cooling into a supersolid state. So we start with the system of high temperature, and then by forced and plane evaporation, we would decrease now the temperature. And here it's the phase diagram at finite temperature is unknown. Okay, it's completely unknown theoretically how to enter. So what is really the phase transition and the dynamics when you decrease temperature and enter in the supersolid state. And this is what we wanted to understand, and we also wanted to understand, so we know that the supersolid have both phase coherence and translational breaking. And those are two different symmetry which are broken. But when our initial state is a thermal gas, which have non-phase coherence nor translational breaking of the translational symmetry. So, and we wanted to understand in this case if the two symmetry are broken at the same times, or if one get broken before and why. While in the interaction quench, we already start with one symmetry, which is the gauge one given by the global phase coherence of a BC. And so we just have to break one. So it's completely different point of view. And now we have done this experiment here, and with usual in an optical dipole trap with usual forced and plane evaporation. And while we cool down, of course, the population of the mode is changing, and this is with our in situ image. You see a thermal cloud and the direct evaporation in this supersolid state, and then now I'm just repeating from the thermal in situ, it's so low density that you see almost nothing. And then we could follow really the evolution. And so for each of this line is an absorption image. And you see that at the beginning, so we decrease the depth of the dipole trap, and then we look at the state after some thermalization time. This is a thermal state with very low density. We see almost nothing in the in situ imaging and in the phase contrast imaging. And then after a while, we start to see that there is the appearance let's say, of droplet or peak. And then at the beginning, at early time, they are very fluctuating the number of peak, but then later you can really see that the system establish a very specific number of density wave or droplet. And also this state is incredibly long-lived. I mean, this is 1 second, and actually the lifetime is long, so they survive much longer than 1 second. And then, yes, it's fairly long-lived. And we could now, so we see by in situ the appearance of density modulation, and we can also equally look by interference pattern, as I commented before, the appearance of phase coherence. And basically, this is maybe not so easy to get immediately an intuitive picture, but when we have the time of flight, we do a Fourier transform, and we see at the K corresponding to the peak, and we can define a phasor which have a phase and an amplitude. The amplitude, this is the phasor from the Fourier transform. The amplitude is telling you about modulation and local coherence within a droplet, and the phase is telling you about the global phase coherence. And from these two quantity, from the phasor, we can define a quantity which we call AM, so the amplitude of the modulation, and the phi, which tells you about the phase coherence. And in a more intuitive way, you can look the phasor into this plot, and you would see that when you have a thermal gas, it's kind of the amplitude is either 0 or very, very small, let's say shot noise limited sort of. But then when you enter in a state which have only phase modulation, modulation, but no phase coherence, you see that the amplitude, so the radius of the circle increase. So there is modulation, but there is no preferential phase. And then when you are in a state which have both, you see that the phase is kind of focusing in some given value. And alternatively, you can see this as just thinking, okay, I take this interference pattern 100th time, and then I look whether it's always the same interference pattern, and then it means it's coherent. So if I take the mean, I see the peak, or or it's incoherent. That means that I always see an interference pattern, but the peak are each time different. And then in the average, I see nothing. And this is also a way to visualize both AM and AFI, which I have defined before. So when we studied this type of dynamics, what we saw is that at the beginning of the evaporation, when the system is thermal, let's say both the modulation and the phase are absent. Here, the fact there is an offset because of just technical, we didn't want, to rescale the data. But then at some point, we see that the modulation starts to increase while the phase coherence still seems to be pretty low. And so here it appears that when we go to the supersolid state, we have first the development of density modulation. So the translational symmetry is the one broken first, and only later phase coherence is established into the system. And the reason why they are not simultaneously this breaking of coherence is actually an open question, which we hope together with theorists to be able to understand whether this region is a region connected with quasi-condensation or with high population of low K mode, or whether it's connected to the compressibility of the system. It's really an interesting open question that we hope to get. Now, as I said, we have also the depth of the supersolid. So here it's our supersolid state, and then this dye, and we can follow what is the full life cycle of a supersolid. From a thermal, it seems that the system goes in a quasi-condensate, then it becomes supersolid, and then eventually at some point, three-body losses kick out, that the number of coherent atoms goes down, and the system goes from a supersolid to a BC. So, Alicia, I see you. I should close.
I was actually going to relay a question, although I think you covered half of it. So Paul Julian wanted to know if the 1 second lifetime in your recent experiments comes from three-body recombination or something else, and if there's anything interesting about three-body recombination in supersolids.
Okay, so Paul, I think as usual you touched on an extremely interesting question, and I don't have the answer. In which sense? When we have an ordinary Bose-Einstein condensate, we are always thinking that three-body losses are occurring at the center of the trap, because there the density is higher, and so we always think that it's the coldest atom, which are the one at the center of the trap, which are the one lost in three-body recombination process. Now, in the supersolid, it's completely different, because now there is no, let's say, it's not that at the center you have the coldest atom. Actually, maybe at the center you have zero atom, because you have now this density modulated. So you might lose the highest, let's say, density atom, but this does not necessarily connect to the coldest one in some sense. And so it's not really clear for us. We cannot how to model three-body losses in a supersolid, because you need the density profile and how to do. Anyhow, in our specific isotope, which is special really to our experiment in Innsbruck, you have a lifetime which is extremely long. I mean, you see here it's 2 seconds. You still see some structure, or a little bit before you still see some structure here, and at the end, indeed, when you lose atom because of three-body losses, but you don't end up with a thermal sample as you would imagine in ordinary BC. We actually end up at very long time with a little Bose-Einstein condensate. You see, this is a little Bose-Einstein condensate, and we have also another imaging that where you can see very clear that this is a condensate. So it's an open question that we need to understand yet. And so if now I have...
well, could I ask, this is Charles, could I ask a question just following on Paul's?
Yeah.
So I would think, so the body proportional to some power of the density and a coherence factor like a G2. Are those any different in a supersolid than they are in, say, a normal Bose condensate? That is, does the density coherence function, does that change between a condensate, pure condensate, solid?
Yeah.
And does a supersolid support higher densities than a normal condensate?
Yeah, so the supersolid support higher density, let's say easily factor an order of magnitude higher density. This is each droplet. The G2 question, I mean, in ordinary BC with moderate scattering lengths, let's say 100 A0, doesn't play a big role. I mean, from thermal cloud to Bose-Einstein condensate is always this factor of 3 factorial. While, I mean, there have been experiments with higher scattering lengths where this 3 factorial was changing, okay, because of the larger correlation. Now, what it is in a supersolid, we really don't know. I mean, we don't have a description of the state. So, you know, I can measure L3, the 3-body loss coefficient in the thermal cloud. This I can do. But then how these will transport in the condensate supersolid, I have no idea. And I think I'm not aware of any theoretical prediction or work on this. You know, whether I can simply use, I mean, we use the 3 factorial. So we measure thermal and then we use the 3 factorial. But to be honest, from what we see in the experiment, doesn't fit very well somehow. So somehow the losses that we see are smaller than the 3 factorial. We didn't do a very specific, let's say, you know, a consequent study really to be able to say 100% is like this. But for few magnetic field that we saw, I mean, doesn't seem that everything fit really 100% with the 3 factorial. Yeah.
Okay, thank you very much.
Yeah. Okay.
One quick question, if I could follow up, Francesca, on my question
sure.
about the 3-body. Can you do any quantitative measurements at all of 3-body, or is the situation or the densities too low or something, or it's hard to get a quantitative handle on it?
So as you know, what I can do, I can measure the evolution of the atom number as a function of time. Now, the rate equation depends on density. How do I convert atom number into density? Well, if I have a Bose-Einstein condensate or a Gaussian function, I know what's the volume is. It's easy. What do I put for the supersolid? I cannot put the volume of the trap. Will simply not work. I mean, this is a modulated state. And here's where the trouble starts. So I can certainly very precisely follow the evolution of the atom number in temperature. But then I need to go to a density. Does it make sense what I am saying?
Yes. Do you have an estimate of how many atoms per supersolid cell you have in your real experiment?
Yes, we can fit this, and actually the GPA also kind of agree on how many atoms we have in the supersolid. Yes. Yeah.
What is that number? Is it more like hundreds or thousands, or what would it be?
Yeah. So we have
Tens?
have about, for the latest measurement that I will show you now, we have about 10 to the 4 atom per droplet. And the density is actually pretty high, but I have not estimated that. It's about 1 order of magnitude larger than the normal BC density. So they are very squeezed.
Okay, thank you.
Yeah.
So sorry, to clarify this for myself. So basically the issue is that the shape of the cloud is changing in time, and 3-body loss is very density dependent. And so you would need like the local density as a function of time to try to match everything. And that's so much data. Okay.
Somehow, yes. Somehow, I don't know how to. So there is. I mean, of course I can put a sinus function. So if I have a density distribution, let's say whatever it is, our density distribution, I can say, okay, I have a sinus function, and I can estimate with the sinus function. You know, I can have a Gaussian and put a sinus function on top. And then say, okay, this is my density distribution. And from this, I can get some L3. This I can do. But it's not extremely accurate. That's the problem. Then, I don't know, maybe something better should be really developed. Because, and also it's a soft object. And so you would maybe lose preferentially from some high density peak that on the side, but this also will mean because it's so highly correlated that the droplet will rearrange completely. So you will have maybe flow on another droplet side. So it's not stiff. By any means is a lattice system. It's not stiff, and so they can flow to try to rearrange and agree with the chemical potential. So that's why there is a dynamical effect. This non-equilibrium part of three-body losses would be extremely important, which we typically forget with a normal, let's say, Thomas Fermi or Gaussian cloud. Okay, maybe now if I have a few minutes or not.
I think you have a few more minutes. Yeah,
okay,
we started a little late and we delayed you. So, maybe 5 more minutes.
Yeah, 5 would be more than enough. Now, I want to show you something which is really a work in progress, because one of the main outlook in this super solid was, okay, let's say, driven by the idea that the state that we saw, first of all, is small, but this we cannot do too much. And second, you break the translational symmetry only in one direction. So it's uniaxial. So it's not a 2D supersolid, it's really just a 1D. And one of big outlook was actually to try to go to 2 dimension, to go more close to what it is really a bulk supersolid. And this is, many theoretical work have suggested that 2-dimensional supersolid can exist, but for an atom number much larger than what typical experiment can have. And so this was a kind of not much impossible larger, but still larger than what we have. And this was a kind of a sort of stop in let's say, in the progression of experiment in this direction. But actually, we got very much inspired, thanks to Luis Santos, with whom we are collaborating, and Russell Bissett, very much inspired by something that you can observe in ion. So in ion, there is a structural quantum phase transition from a linear change of ion to a sort of more, let's say, off-axis zigzag type of distribution. And so the ion do this structural quantum phase transition just by changing the transverse confinement of the ion. And so inspired by this very nice first observation in '92, and then also many experiment and theory over the year, the question is whether we can have something similar in our supersolid state, use the transversal degree of freedom to try to cross the structural phase transition. And so this is now what we did, and to do this, what we need is a trap which is neither pancake nor a cigar, is what we consider to be a surfboard trap geometry. It's really, let's say, a surfboard, and one has to be able to scan in a way that we can change the size of our surfboard. And so by changing the geometry with both a scanning trap that creates time average potential and a static trap, we can change the aspect ratio of our trap. And we were able to really improve our setup and to have a lot of coherent atom number with respect to previous. And what we see by just changing the trap is that our linear chain notice, now we even have much more we have more droplet than before. By changing the aspect ratio, there is a specific value of the aspect ratio in which the system start to, the central droplets start to split. And this is for me, super interesting, because it seems that this droplet at the middle now experience a lot of repulsion from this gigantic magnet here, which is one droplet, and this gigantic magnet here is squeezed between two high density magnet. Is really like having a mesoscopic magnet, and it gets splitted if the trap is allowing, and then this type of zigzag geometry start to appear more and more, and at the end what you start to have is moving really from a single axis to something which is more two-dimensional. And this type of measurement is extremely robust. So in the first here row you see single image, but then in the row below it's all average image. I mean, over 40 shots, I think, each of these, and we don't recenter, we don't do post-selection, we don't do anything. We just take the image, put one on top of the other, and average, and you really see still that this type of structure survives amazingly stable. And then, I mean, here is a zoom in of what is the structural phase transition, and notice here is sort of a triangular type of geometry, and this is important that it's triangular for what I will tell you in a moment. It's really, let's say, more going into 2D, and we can estimate what is the critical aspect ratio by plotting let's say, not caring about the droplet, but just, let's say, making a total aspect ratio of the cloud and plotting it against the trap aspect ratio. You see that really when you're in the supersolid state, there is a critical point in which the system starts to go two-dimensional and create this type of zigzag transition. And for an unmodulated BC, you don't see none of this kink. And then the second question is, now this 2D structure, is it phase coherence? And now, if you remember what I told you about the repetition, no? That if the interference pattern is stable, then this tells you about phase coherence. This is really the average picture for our 2D supersolid, which have a six-fold symmetry. That is exactly what you expect for a triangular type organization, and it's an extremely robust and stable interference pattern. And actually, it is exactly what you would imagine by simple simulation, this six-fold type of symmetry. And if you have instead the incoherent droplet that we could also create both in simulating and in the experiment, you see that this clear interference pattern is washed out. So we are very happy about this new result, and it's very encouraging to us to move more and more to work bulk to the supersolid state. And this ends up a bit my talk. Of course, we have many other studies going on at the same time in the labs. We have produced the Erbium and Dysprosium quantum mixture and study dipolar mixture, which is also a lot of fun. And we have now with Erbium also studied a type of clock type transition, which is an inner shell transition where you promote one of these F electron to a D electron while the outer shell is unchanged. And this is quite very nice for optical control. We can look at the Rabi frequency. We can coherently manipulate the atom using this inner shell orbital transition, which is about 2 Hertz in a very nice wavelength region for the experiment. And finally, we have now also the first spectroscopy of Rydberg atom of erbium, in which we can clearly identify the S series and the D series in multi-electron Rydberg atom. And with this, I would like, to of course say that nothing all of this is possible without the great team I had the privilege to work with in the last years. And now we have also developed, we have the Erbium lab and the Erbium Dysprosium lab, which are the one for most of the results I showed you with the leading postdoc Matthew Norcha. And we have the Rydberg experiment, which is in with the first spectroscopy, and now also we are building up a little theory team, which is helping us enormously in understand the physics. And with this, I would like to let's say thank you for your attention, and of course we have opening if some student is interested to join for a PhD, postdoc, or just for an internship, we would be happy. Thank you very much for your attention.
Thank you very much. That was a wonderful talk. So the floor is now open for questions.
Francesca, this is Bill.
Yes.
Throughout the talk, you've been using phase coherence as an indication of superfluidity. But of course, what superfluidity is really about is frictionless flow. So what about that? And could you say something about critical velocity in a supersolid?
Yeah. Yes, actually, so first of all, we were also thinking a little bit, okay, what is the relation between superfluidity and phase coherence? Phase coherence and I realized that in alkali Bose-Einstein condensate, Bill, maybe you would agree, this is almost given for granted that you have a BC and this automatic superfluid. But proof of superfluidity, I think Gretchen with the persistent current is one of the few experiments really measuring superfluidity.
Yes.
And this is where we should go. I mean, because we were searching intensively, on proof of superfluidity, superfluid flow. I think we do have, for example, when I show you the spectrum of excitation, there is a kind of a Josephson current that we can measure. I had no time to show other experiment on this, but we do measure flow, coherent flow in terms of when we excite and the population move from one side to the other. But the superfluidity, this flow should be stationary. And I think Gretchen was the only one.
Yeah.
And this is what we should do, a ring trap. But
Well,
it's not so trivial.
Well, exactly. Well, one of the things I'm wondering is, what do you expect for a critical velocity? I mean, of course, critical velocity is one of these things that a lot of people talk about, but very few people measure. And it depends on the density. And you might guess, for example, that the critical velocity would have to do with what the minimum density is between the connected droplets. But I'm wondering whether you've thought about that or calculated anything.
So we have the spectrum of excitation. So at low momentum, so for ordinary BC, you have your, let's say, phonon regime, and the slope of the phonon is the critical velocity, or the sound velocity, let's say. And these two slopes, actually, from there, you would expect two different critical velocity. And you would expect that the superfluid or two different sound velocity, the crystal sound velocity and the superfluid sound velocity. And the superfluid sound velocity, more you enter toward the disconnected droplet, it kind of vanish.
Yeah.
Yeah, because the link vanish. And this we see. So we see certainly very clearly in our calculation, and in the experiment we do see an decrease of the response of the system. Yeah.
Okay.
Yeah. Is there any question on the chat, maybe?
So there was one question about how exactly specifically you soften the Roton mode in the experiment.
Yes. So So these lanthanide atoms have another feature with respect to the one I discussed. And one is that they have an incredible number of flashback resonance. So this means that by changing the magnetic field, we can change the value of the scattering length, and this is what we do. And since these atomic species, both erbium and dysprosium, have many flashback resonance, we can actually work nearby the most convenient flashback resonance. And so, and in this way, we can reduce the value of the scattering length. And yeah, and so, and boost the strength of the contact interaction.
Mm-hmm. And so then the challenge there was to get the magnetic field control fine enough to really tune exactly to the point that you needed to be at?
Actually, no, because actually this was pretty easy because the resonance had very low magnetic field. So it's very easy to control small magnetic field. I mean, let's say if you think rubidium as a resonance of 1000 Gauss. This is super challenging, you know, but we have resonance at 1 Gauss, 2 Gauss, 10 Gauss. So from 0 to 10 Gauss, we find so many resonance and we move there. So it's not so difficult to have very high precision at low magnetic field.